Here is a video walking through example 5.2 in the book that describes this manufacturer of small kitchen and home appliances. They use a metal sheet bending machine to make cases for their wide range of small and medium-sized electrical ovens that are produced to order, so built to order. If there's a large difference between the size of the current and the next case, the worker needs to perform a setup to make the machine ready for the next case. Past data show that the worker performs a setup after processing an average of 6 cases, with the probability of needing a setup after finishing a case to be almost the same. The setup takes an average of 6 minutes with a standard deviation of 3 minutes. The time to make a case of any size has an average of 2 minutes, standard deviation 1 minute. The firm is considering the following two approaches in their lean operations initiatives to reduce setups. First option is setup time reduction. Reduce the setup time by using additional offline tools and fixtures. This will reduce the average setup time from 6 minutes to 3 minutes with a standard deviation of 1 minute. However, the setup will be performed more often after processing an average of 3 jobs instead of 6. Setup elimination is the second approach. Redesign the cases such that there would be no need for setups. This, however, increases the theoretical mean process time at the machine from 2 minutes to 3 minutes and the standard deviation from 1 minute to 1.5 minutes. How do the above two approaches affect the performance of the bending machine? So let's start with the information that we know. This is example 5.2, and we have some information that we know. We know that the theoretical time is equal to 2 minutes. Theoretical mean process time. We also know that the standard deviation, let's see if we can add our standard deviation here, is 1 minute. And this is theoretical standard deviation time. And I'm getting that from right here. The time to make a case of any size has an average of 2 minutes with a standard deviation of 1 minute. We also know that on average it takes about 6 jobs between setups. So our N here is the number of jobs, about 6 jobs. And then we also know what the setup time is and the standard deviation of that setup time. So let's put that in here as well. Here's our setup time, 6 minutes. And our standard deviation, actually I'll just do this one. Of the setup time is 3 minutes. Setup times standard deviation. And so we're looking at performance for each of these two approaches. One of the first things we want to do is calculate our effective capacity. So let's look at the effective capacity from a from this perspective, which is we'll take the theoretical mean process time of 2 minutes. We will add that to the setup time divided by the number of setups, and that is 3 minutes. So the effective mean process time is 3 minutes. These come from some equations right up here, right above, where it says in these particular activities, this is a task-based interruption. So this is saying after 6 jobs, Every 6 cases, that's our N. So we're using these formulas to find out what our effective mean process time is so that we can figure out what our effective capacity is. So let's do that. Let's do our effective mean process time is equal to a theoretical, which is 2, plus the setup time divided by the number of jobs. And that is going to be 3 minutes. So this is our effective mean process time. And now we can take that and create the capacity. What is the capacity? We can do 60 divided by that, which gives us the number of jobs per hour. Effective capacity in jobs per hour. Okay, so we're doing 3 minutes effective mean process time. We're doing 20 jobs per hour. Now we can use that to compare another approach. This is kind of the current capacity of this metal sheet bending machine. So let's look at setup time reduction. So under setup time reduction, we have a couple of changes. So let's do a setup reduction section here. Setup reduction, setup time reduction. And what's changed here is we have an NS of 3, which means that the average has changed to about every 3 jobs. We have a setup time that's shorter, 3 minutes. New setup time. And we have a, so it says, thus the machine will have effective mean process time of this, resulting in the same effective capacity per hour. Sorry, excuse me. We're down, wait, where are we? Yeah, under the setup time reduction, we have NS of 3, TS of 3. Thus, the machine will have effective mean process time of 3 minutes. So let's calculate that right here. What is our new mean effective process time? Well, it turns out we still have the same theoretical time. We're adding to that the setup time, which is down to 3, and we're adjusting for the number of jobs between setups, and that is also 3. So this is our new effective mean process time. Turns out it's the same. And if that's the same, then our capacity is also going to be the same. 20 jobs per hour. Okay, so it turns out that this new setup approach, this new setup time reduction approach, this first approach here, does not actually impact capacity. It doesn't go up or down. It's actually the same capacity. If the setup operations is eliminated, we have a theoretical setup time of 0. However, the theoretical mean process time of the machine is increased to 3 minutes. Since there are no setups, the effective mean process time of the machine would be equal to the theoretical mean process time. This results in the same effective capacity of 20 jobs per hour. Okay, so let's walk through this one. This is the setup elimination option. And what this is saying is, if there's no setups, this is this one down here, setup elimination. If there's no setups, then TS is equal to 0. TS is equal to 0 minutes. There's no setup, which makes sense. However, the theoretical mean process time increases to 3 minutes. 0 setup time. Additional theoretical mean process time. So it's taking us longer to produce. We're going from this 2-minute theoretical mean process time to 3 minutes in this particular approach. And that's where this 3 is coming from here, is it's saying it's 3 minutes there. But if we do the calculations again for effective mean process time, what is that? So the effective mean process time is going to be the theoretical plus, this time we have no setup time, so it doesn't matter how many jobs we have. Even if we go up to the 6 jobs here, it's still going to be 3 minutes. And if the mean effective process time is 3 minutes, that means the mean effective capacity is still 20 jobs per hour. Okay, so basically what we've seen so far is that we have these two approaches, and neither approach negatively affects capacity or has any impact on capacity. So maybe it doesn't matter. Well, we shall see. There's a couple more iterations that we can make here. A couple more ways to look at the performance, how the performance changes. So the book says the two approaches do not affect the effective capacity of the machine, but they certainly impact the effective variability. For the current situation, the variance of the effective process times can be computed using equation 5.8 as follows. And let's just walk through this equation here. I'm going to go ahead and copy this into my spreadsheet, mostly for future references, just so I can see what this looks like here. And when we plug in the numbers here, this is for the variance of the effective process times can be computed as follows. So let's look at this one. Let me go ahead and put this here. I actually like to put a little border around it so we can see a little bit clearer. And we need to figure out all these inputs so that we can calculate this, right? It'd be fun to do a VBA script on this too. That'd be sweet. Do we have all this information? I think we do. Let's figure this out. So, in fact, let's come up here. Maybe it would be helpful to do up there because all the data is up here, but that's all right. We'll refer to this up there. We have equals to, this is our standard deviation of the theoretical process time, which is right here. 1, and we're going to square that. 1 squared plus, now we'll do the standard deviation of S, which is the standard deviation of the setup here. We'll square that. Whoa, what happened? I lost it. Plus, here's our standard deviation of the theoretical process time squared, plus the standard deviation of the setup time, which is 3 minutes, squared. We'll square that. And what I'm doing is I'm just following along right here, right? I'm putting these numbers in here. We've got the 1 squared plus the 3 squared divided by the NS, which is number of jobs, which is 6. Let me go ahead and reference that. Plus, open parentheses. Let me do open parentheses again. And we have the NS again, minus 1. So it's going to be 6 minus 1 divided by NS squared. I'll square that. Close parentheses. Times, and then we have a TS squared. So here's our TS squared. This is our TS. This is our setup time. We're going to square that. And what does this equation give to us again? Why are we doing this? This equation is going to give us the variance of the effective process time. The variance of the effective process time. So we have capacity. We have the mean effective process time. What we haven't calculated yet is the variance of this effective process time. And that's what this equation gives us. So we'll hit enter on this equation. That gives us 7.5. What does that mean? Well, nothing yet. We still have to take the square root. So this is, in fact, let me move this here. So we have, this is the sigma squared. So we will insert the sigma squared. And this is the effective. So let me see if I can do this. Oh, we'll do superscript. We'll do subscript. This is the sigma squared of the effective process time. And so to get the square root of that, we simply take the square root of, let's see, sorry, the coefficient of the variation is this, the standard deviation divided by the mean. We take the square root of the 7.5 to get the standard deviation, because right here it's squared. So we're simply taking the square root of that divided by the mean, which is 3, and that gives us our coefficient of variation. So let's do that right here. Let me go ahead and do this guy. I'll copy this down, and we'll take out the squared. So we'll do the squirt of the 7.5. And then we'll do the CV, the coefficient of variation. And this is for the effective process time, is equal to standard deviation divided by the mean. And the mean we found out to be is 3 minutes. So we're taking this square root of 3.75, or excuse me, square root of 7.5 divided by the 3, and that gives us this 0.91, and there it is. So we've come up with the effective variability of the machine, which is 0.91. Let me do something, let me do a subscript here, and that makes that a little bit more palatable, I think, or agrees more with the book. Okay, so now that we've done that once, now what happens if the mean setup time is reduced to 3 minutes? So now we're taking, again, we're going back to this first approach, setup time reduction. We're saying if that setup time is reduced to 3 minutes with standard deviation of 1.5 minutes, and the setup operations needed after an average of 3 jobs, what is the variance of the effective process time? Doing a very similar equation we just did for the current process up above, we're finding out what is the effective variability of the machine if we're going to follow this mean setup time approach. So let's do that. So this is going to be the mean setup time approach, or excuse me, setup time reduction approach. And we're going to use the same formula. Yeah, now I'm starting to think maybe we should move this over here just to make this all just a little bit closer. You know what I'm saying? Just a little bit closer together. So I'll move this up here. Just to keep this, this is the current process. This coefficient of variation is for this current process up here. We're now working on the setup reduction effective variance. So let's do this one down here. So we'll copy these cells down here. And we'll do the calculation again. We'll use the same formula, but this time we're going to take into account a little bit different inputs for this setup time reduction scenario. So what is this equal to? This is, again, we're going to take the theoretical standard deviation of the theoretical mean process, which is 1 squared, plus the standard deviation of the setup time, which is 1.5 minutes. Okay, it's important to note here too that the standard deviation has changed. I did not include it here. So let me go ahead and include that here before we get too far going here. This is the standard deviation of the setup has changed to 1.5 minutes. So again, if we come back up here, this is saying if we eliminate the setup, yeah, so apparently there is a little bit of a misconfiguration here. Um, we're going to use what this number is down here for the standard deviation for the mean setup time reduction option, not for the elimination, but for the reduction. In other words, what we're looking for is we're still trying to figure out this equation right here. We're looking for the standard deviation of the setup. Here it says 1.5 minutes, so we're going to go ahead and go with what it has right here in this portion of this example. Up above, I believe it says 1 minute, but we're going to use the 1.5 minutes here to follow along with the book in these equations. But I think it's also important to note that often when you reduce some kind of time as the average, it's not uncommon to see the standard deviation increase. So I think it's actually more realistic if the standard deviation increases to 1.5 minutes instead of uh, instead of the 1 minute up above. So we're going to assume here that the standard deviation for the setup, so this is going to be another standard deviation of the setup, is equal to 1.5 minutes. Now that we have that in our setup time reduction option, we've reduced our setup time and our standard deviation of the setup is 1.5 minutes. Now we have all the pieces to identify the variance of the effective process time. So let's figure out what this variance is. Again, we're going to start with the standard deviation of the process time, which hasn't changed. That's up above at 1 minute. We'll square that. We're going to add to that this expression, which is the standard deviation of the setup time. We'll square that. We'll divide by ns, which has changed to 3. We will add the ns minus 1, all divided by the ns squared times ts, which is the setup time, the new setup time squared. So when we do that, we get 3.75. So we are aligned here with the book. Again, this is the variance, and the effective variability is the CV. So we take the square root, we take the squirt of the variance, that gets us the 1.94, and the effective variability, which is the coefficient of variation, is going to be the standard deviation divided by the effective mean time. And that is 0.64. We have 0.65, a little bit of rounding difference. The book does not take into account more decimals beyond 3.75. So we're a little bit more accurate than the book, but we're there. We have the effective variability of the machine. So if setup operations is completely eliminated, the effective variability of the machine is equal to its natural variability, which is, so we're doing the setup elimination option now, and if we look at the variation of the setup elimination, that's what this paragraph is telling us. If the setup is completely eliminated, then the effective variability of the machine is equal to its natural variability, because there's no variability on the setup. And the natural variability would be the equal to this equation here. So we're going to do we're going to take the standard deviation and we're going to insert the standard deviation, and basically it's the theoretical, so it's a naught, and that's equal to, we've got that up here, the 1 let's see, so this says the standard deviation of the theoretical process time is 1.5. And that is true. So if I come back up here to the setup elimination process, the standard deviation has gone from 1 to 1.5. So we can include that here as well. This is the standard deviation of the mean process time is 1.5 through the setup elimination process. So if that's that, then we can come down here and figure out this formula, which is the effective variability, given that there's no setup. We already have our standard deviation of the theoretical process time. We have our average time of the theoretical process time. We can use those to find out the effective variability from an effective process time, because again, there is no setup. We've removed setup, and this is the effective and the theoretical variability. So what does that look like? Let me copy my symbol down here, and this is going to be equal to the standard deviation divided by the mean time, and that gives us 0.5, which is lower than the setup time reduction option. The book also says, before we conclude our discussion, we must emphasize the following. In the above example, setup time reduction or setup elimination did not affect the effective mean process time and thus did not change effective capacity. We've talked about that before, right? In both situations, the effective capacity is still 20 jobs per hour. In most cases, however, setup time reduction or elimination does reduce the effective mean process time by reducing or eliminating supporting task times, and thus results in increase in effective capacity. That is one of the reasons that setup time reduction is one of the most important tools of lean operations. Also, comparing the machine's current situation with the option of reducing the setup in the above example, we reach the same insights as in time-based interruptions. If the theoretical and effective capacities remain unchanged, more frequent interruption, but with smaller length of interruption, is preferred over less frequent interruption with longer interruption time. Specifically, in the current situation, the average time between two interruptions is longer than under the setup time reduction, time to produce an average of 3 jobs. However, the interruption time in the current situation, average setup time of 6 minutes, is longer than that under the setup reduction option, average setup time of 3 minutes. So, setup time reduction resulted in lower effective variability. The book concludes with this principle: more frequent but short interruptions result in lower effective variability than less frequent but long interruptions, given that capacity, theoretical and effective capacity, is unchanged. Hopefully that's helpful to walk you through this example. Let me know if it helps and what other questions you might have.